In intense, fast-paced, maneuverable dogfights, where split seconds often count, a fighter pilot physically does not have time to take his eyes off what is happening outside the cockpit, searching for the right switch or button on the instrument panel. It was this fundamental problem that led to the development of a concept that radically changed the ergonomics of the cockpit of a modern combat aircraft: HOTAS, hands on throttle and stick. The essence of the concept is to place the maximum possible number of controls most commonly used in combat, switching radar modes, selecting the type of weapon used, controlling the electronic warfare system, shooting false thermal or radar targets, and many other functions critical in combat directly on the aircraft control stick itself and on the engine control lever, the very two main controls on which the pilot's hands are already located almost constantly throughout the flight. Such a solution allows the pilot to perform most of the actions necessary in a fast-moving battle without taking his hands off the main controls of the aircraft and, what is critically important, without diverting attention from visual observation of the surrounding air situation outside the cockpit in order to search for the desired switch on the instrument panel. The development of such a concept occurred gradually over several decades. The first fighters had relatively few controls directly on the stick and throttle lever, usually only basic functions like a gun trigger and a radio button. Modern fourth and especially fifth-generation fighter aircraft, in contrast, place literally dozens of different multi-function switches, buttons and small joysticks on these two key controls, each of which can perform several different functions depending on the current mode of operation of the onboard systems. Mastering such a complex, multifunctional control system requires considerable time of intensive practice on the part of the pilot to develop the corresponding actions to the level of a fully automatic, muscle skill that does not require conscious thought, just as an experienced musician playing a complex instrument no longer consciously thinks about the position of each individual finger. In parallel with the HOTAS concept, the general philosophy of organizing information in the cockpit of a modern fighter was developing, a transition from many separate, highly specialized dial instruments typical of older generations of aircraft, to much more flexible multifunctional displays capable of dynamically displaying exactly the information that is most relevant to the pilot at a given specific moment in flight, instead of a static, unchanging set of instruments, much of which could be irrelevant in a specific combat situation. The most advanced modern development of this philosophy of cockpit ergonomics has become the previously discussed in detail helmet with an integrated information display system, which allows critical tactical information to be displayed directly on the visor of the pilot's helmet, regardless of the direction of his view, complementing and in many ways continuing the same fundamental idea to minimize the need to divert the attention and physical actions of the pilot from the main task of piloting in combat for the sake of interacting with onboard equipment. We've already talked about how Red Flag and the Top Gun program radically changed the tactical training of American pilots. But who exactly acts as the imaginary enemy in such maximally realistic training scenarios? The answer is specialized squadrons of aggressors, aggressor squadrons, staffed by pilots whose professional task is to accurately imitate the tactics, behavior, and flying style of a potential enemy. The concept of such units was born from the same painful analysis of the Vietnamese experience as the already mentioned Top Gun program. It became obvious that American pilots critically lacked practical familiarity with the actual tactics used by enemy pilots, which differed significantly from their own, well-established American air combat doctrine of that period. Pilots serving in such aggressor squadrons undergo specialized, in-depth training, purposefully studying available information about real-world tactics, standard maneuvers and weapons used specific to specific potential adversaries, rather than simply applying their usual, standard American air combat tactics. In addition to tactical training, the technique used itself is an important element of the reliability of such an imitation. Historically, Aggressor squadrons often used specially modified or intentionally limited aircraft in their flight characteristics, designed to bring the real flight characteristics of a mock enemy as close as possible to the similar characteristics of the equipment of a potential real opponent, which could often be significantly inferior in certain parameters, but superior in other, more modern American technology at that time. The appearance of the aircraft of the aggressor squadrons also traditionally emphasizes their special, isolated role. Instead of standard combat paint, these aircraft often carry non-standard, sometimes very exotic camouflage schemes, designed to most realistically recreate the typical visual paint schemes used in the armed forces of a potential enemy, which further enhances the psychological effect of the most realistic simulation during a training air battle. Service in such a specialized squadron is considered very prestigious and valuable from a professional point of view for a military fighter pilot, since it provides a unique opportunity for the deepest practical immersion in alternative tactical doctrine and flying style, significantly different from their own, familiar, which subsequently makes such pilots especially valuable instructors and tactical specialists, capable of training the rest of the flight personnel in the most realistic recognition and effective counteraction to specific tactics. Probable enemy. Aggressive pilots consciously use real, often very sophisticated tactical tricks and maneuvers during training air battles, deliberately provoking the opponent to certain erroneous tactical decisions, using visual and tactical deception techniques characteristic of a particular potential enemy, which makes such training encounters much more psychologically and tactically demanding for the trained pilot compared to a regular training battle against a colleague using familiar, expected tactics. The experience gained in a collision with the most realistically acting fictitious enemy within the framework of such specialized training programs, as is generally recognized by many military pilots and analysts, remains one of the most valuable elements of the entire modern system of tactical training for fighter aircraft, significantly reducing the psychological and tactical shock that might otherwise arise during the first real encounter with the unusual tactics of a real enemy in an actual combat conflict. Block 3 Radar Hunters. How the mission of suppressing enemies' air defense was born. Equals 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 equals. We have already touched on the topic of electronic warfare and the role of specialized aircraft like the EA-18 Growler. But there is a separate, historically even earlier and in its own way legendary direction of such a struggle, the mission of suppressing the enemy's air defense system by direct fire, which originated during the Vietnam War under the unofficial but historically established name Wild Weasel. By the mid-60s, Soviet anti-aircraft missile systems supplied to North Vietnam began to inflict serious, tangible losses on American aviation, significantly exceeding the initial expectations of the military command. Simply avoiding or ignoring such a threat no longer seemed like a reasonable tactical option. A fundamentally new approach was required to neutralize the threat itself directly at its source. Born in response to this problem, the Wild Weasel concept involved the creation of specialized crews and specially equipped aircraft, whose direct, very dangerous task was to deliberately provoke enemy anti-aircraft missile systems to turn on their guidance radars, thereby unmasking their own location, and then quickly attack and destroy the detected enemy firing position before it had time to launch a missile at the provocateur aircraft itself or at other, less protected aircraft of the main strike group. The pilots and weapons operators who served in these specialized crews acted in accordance with the motto that later became widely known in the military aviation community: first there, last out, eloquently describing the very essence of their extremely risky task, which required a conscious, deliberate drawing of the deadly attention of an enemy air defense system for the protection of other participants in the combat operation. Technically, such specialized aircraft were equipped with a special set of radio reconnaissance receiving equipment, capable of accurately determining the direction and nature of the radiation of the enemy missile guidance radar, which allowed the crew to quite accurately localize the position of the enemy anti-aircraft complex even without direct visual contact with the firing position itself, which was often well camouflaged on the ground. Subsequently, such specialized aircraft also received a special anti-radar missile, capable of independently aiming directly at the source of radar radiation from an enemy radar, significantly increasing the efficiency and, importantly, the relative safety of such an extremely risky mission compared to the need for visual detection and subsequent attack of an enemy firing position with conventional weapons. This concept, which originated in the specific conditions of the Vietnamese conflict, subsequently turned into a permanent, integral element of the general military doctrine of suppressing enemy air defenses, known today under the broader term SAD, suppression of enemy air defense, which continues to actively develop and improve along with the general development of both air defense systems and means of countering them, but keeping unchanged the fundamental idea, originally formulated back in Vietnam, the need for active, offensive counteraction to the threat directly from its source, instead of passively avoiding it. Nuclear weapons carried on board strategic bombers and other carriers represent one of the most serious areas of responsibility in the entire structure of military aviation. How is protection provided against the unauthorized, erroneous, or unauthorized use of such weapons, including the theoretical scenario in which an individual crew or commander might attempt to use a nuclear weapon without appropriate, lawful orders from senior military and government authorities? The key technical solution, developed back in the 60s of the 20th century precisely to prevent such a scenario, was the system of permissive action codes, permissive action link, PAL, a special electromechanical, and later fully electronic device, physically built directly into the design of the nuclear weapon itself and blocking the possibility of preparing it for use without entering the correct secret activation code, unknown to the crew in advance. Before the introduction of such a system, physical security and strict organizational procedures remained the only barrier theoretically preventing the unauthorized use of a nuclear weapon already on board an aircraft or other carrier, which was recognized by the military and political leadership as potentially insufficient protection in certain extreme scenarios. The system of authorizing action codes fundamentally changed this situation, making the ammunition itself physically inoperable without entering the correct code, known exclusively to a limited circle of people of the corresponding highest level of clearance and transmitted to the crew exclusively through strictly defined, repeatedly protected communication channels immediately at the moment of receiving a legal order to use the weapon from the appropriate high command. In addition to the activation code itself, a modern nuclear safety system includes a number of additional technical safety mechanisms, known as single-point detonation reliability and other highly specialized technical solutions that structurally exclude accidental, unintentional detonation of ammunition even in the event of a serious accident, fire, or crash of a carrier aircraft with ammunition on board. A separate important organizational element of such a security system is the so-called two-person rule, which requires mandatory simultaneous, independent confirmation and participation of at least two separate, duly authorized persons at each critical stage of the preparation and potential use of nuclear weapons, which is intended to exclude the very scenario in which a single person, regardless of his formal position or rank, could single-handedly initiate the use of such weapons. This multi-level, multiple redundant system of technical and organizational security measures has been developed and constantly improved for more than half a century precisely with the aim of absolutely reliably excluding the very possibility of unauthorized, erroneous, or unauthorized use of nuclear weapons, while at the same time such a system was supposed to be guaranteed to maintain the ability to quickly, reliably use weapons in the event of actually receiving illegal, properly confirmed order from the highest military and state command, the most complex engineering and organizational the task of ensuring both the absolute reliability of blocking and the absolute reliability of timely unblocking when legally necessary. The internal volume of the fuel tanks of any fighter is objectively limited by the dimensions of the fuselage and wings itself, which imposes a significant limitation on the flight range without refueling. One of the simplest, but at the same time very effective technical solutions to this problem is the use of suspended, jettisonable fuel tanks, drop tanks, installed on the external hardpoints of the aircraft, similar to those on which weapons are mounted. Such an outboard tank is a relatively simple in design container with a streamlined aerodynamic shape, filled with an additional supply of aviation fuel and connected to the general fuel system of the aircraft through a special detachable connection. Fuel from such an external tank, as a rule, is produced by the engine first, before switching to the main, internal fuel supply of the aircraft itself, which allows the pilot, in the event of a sudden need to immediately enter a maneuverable air battle, to dump an already empty or partially empty external tank, instantly getting rid of the associated aerodynamic drag and, importantly, from the risk of possible fire or damage to the tank itself during subsequent intense combat maneuvers. It is the possibility of a quick emergency release of such a tank in a critical situation, a technical feature structurally built into the mounting of the drop tank itself, including pyrotechnic or purely mechanical locks that can almost instantly release the tank from the suspension point at the command of the pilot, that represents a critical element of the safety of this technical solution. A significant aerodynamic and tactical disadvantage of using outboard fuel tanks is a noticeable decrease in the maneuverability and flight characteristics of an aircraft carrying such an additional external load, which makes it extremely undesirable to enter into a maneuverable air battle with the outboard tanks not yet jettisoned, especially fully filled, which significantly increases aerodynamic drag and shifts the center of gravity of the aircraft. In addition, for stealth aircraft, outboard fuel tanks create an additional and very serious problem of the previously mentioned noticeable increase in the radar signature, since such an externally suspended object inevitably creates a much stronger radar reflection compared to the outer surface of the aircraft fuselage itself, which is carefully designed for minimal visibility. That is why fifth-generation fighters such as the F-117 and F-35 tend to use external drop tanks exclusively in missions where maintaining maximum stealth is not a priority, preferring, in conditions requiring maximum stealth, to limit themselves exclusively to internal fuel reserves, even at the cost of a certain reduction in the overall flight range without refueling. There are also more complex, technically advanced versions of this concept, the so-called conformal fuel tanks, built much more tightly and aerodynamically streamlined directly along the contour of the aircraft fuselage, rather than suspended on a separate external pylon, which makes it possible to achieve a certain compromise between the additional fuel supply and a relatively moderate increase in both aerodynamic drag and radar signature compared to classic drop tanks of a traditional design. Although they do not completely eliminate such disadvantages. While most branches of military aviation focus on direct combat applications, there is also a very unusual, highly specialized branch of military aviation whose direct mission is not to confront a human enemy, but to directly, intentionally fly directly into the center of one of the most destructive natural phenomena, a tropical hurricane. Specialized Air Force and National Guard reserve units, equipped with modified transport aircraft such as the WC-130, regularly fly reconnaissance flights directly through the structure of emerging and mature tropical hurricanes, collecting critical meteorological data not available through any other currently available surveillance methods, including satellite reconnaissance. The main task of such flights is the most accurate determination of the center, intensity and structure of a particular hurricane directly from within the storm itself, including accurate measurement of atmospheric pressure in the very center, the so-called eye of the hurricane, the strength and direction of the wind at various altitudes inside the storm structure, as well as the general geometry and nature of the development of the cloud structure of the hurricane itself. Such data, collected directly from within an actual storm, is significantly more accurate and detailed than indirect estimates obtained solely through satellite observations from outside the cloud structure, and plays a critical role in modern models for predicting the future development and likely path of a hurricane, directly affecting the timeliness and accuracy of decisions about the necessary evacuation of the population from the potential impact zone of an approaching storm. Technically, such a flight poses a significant challenge even for an experienced crew. The aircraft is forced to overcome zones of extremely intense turbulence, powerful upward and downward air currents within the storm structure, significant changes in atmospheric pressure, and, often, intense rain and hail, which significantly limit visibility and create additional physical stress on the structure of the aircraft itself. The crew of such specialized aircraft undergoes separate, highly specialized training specifically for flights in such extreme meteorological conditions, which differs significantly from the standard training program for most other types of military transport aviation, focused, on the contrary, on the maximum avoidance of such dangerous meteorological phenomena, which has already been discussed in detail earlier. Despite the apparent paradox of such a mission, the deliberate, regular flight of a military aircraft directly into one of the most dangerous natural phenomena, instead of naturally avoiding it, such activities have been making a critical contribution for several decades to the protection of civilians from the devastating effects of tropical hurricanes, clearly demonstrating that military aviation infrastructure and accumulated decades of experience in flying in difficult weather conditions can find applications far beyond the purely military confrontation with humankind. To the enemy. On the 27th of March, 1999, an event occurred over the territory of what was then Yugoslavia, which became one of the most thoroughly studied and truly significant cases in the entire modern history of military aviation, the American stealth aircraft F-117. The same once absolutely classified invisible aircraft, the early history of which we have already discussed in detail, was shot down by an anti-aircraft missile fired by an outdated one by the standards of that time with a Soviet-made Yugoslav anti-aircraft missile system. This event came as a real shock to a significant part of the military and expert community, since the aircraft, specially designed specifically to minimize radar detectability, was successfully hit by enemy forces that formerly had significantly less modern air defense technology compared to what this stealth technology was originally developed against. A subsequent detailed analysis of this incident revealed a combination of several interrelated factors, none of which individually would probably have been sufficient to successfully defeat such a target, but together they created that very, relatively rare window of vulnerability, which the experienced Yugoslav crew of the anti-aircraft missile system was able to take advantage of. Firstly, an important role was played by a certain predictability of flight routes, due to the repetitive, relatively regular nature of the air campaign being carried out at that time. The Yugoslav Air Defense Forces had the opportunity over a certain period of time to accumulate observations of the characteristic routes and time intervals of NATO aviation flights, which made it possible to place a specific anti-aircraft complex in advance in a position that increases the likelihood of successful interception. Secondly, specific weather conditions at the time of the attack were of a certain importance, as has already been discussed in detail earlier in the context of the general principles of stealth technology. The effectiveness of a radar-absorbing coating can decrease under certain weather conditions, including high humidity, which theoretically could slightly increase the real radar signature of a particular aircraft at a specific moment of attack compared to optimal, ideal conditions. Thirdly, And this was emphasized especially persistently by many subsequent analysts. An important role was played by the tactical flexibility and professionalism of the human factor on the part of the enemy, the commander of a specific anti-aircraft missile crew, instead of the standard, predictable mode of continuous operation of the tracking radar, used non-standard tactics of short-term, literally for a few seconds, turning on the radar immediately before the missile launch, thereby minimizing the time during which a working radar could be detected and, accordingly, attacked by electronic countermeasures or destroyed by specialized air defense suppression aircraft, which we discussed earlier in the context of the Wild Weasel mission. This incident served as a serious reason for a deep revision of the general tactics of using stealth aviation throughout the world, clearly demonstrating the most important principle, which was repeatedly emphasized in the previous parts of this material. Stealth technology significantly reduces the likelihood of detecting and hitting an aircraft, but fundamentally does not guarantee absolute 100% invulnerability, especially with a certain combination of factors unfavorable for stealth and high professionalism, tactical flexibility, and successful coincidence of circumstances on the side of the defending enemy. This incident also served as a valuable practical reminder of the critical importance of constantly varying the routes, altitudes and time intervals of air operations, rather than a predictable, regularly repeating pattern of actions, which greatly facilitates the adversary's preparation for a successful countermeasure, regardless of the formal technological superiority of the aircraft used. We have already discussed in detail the fundamental tactical logic of flying in pairs. But the real tactics of group flight are much richer than simple division into pairs, including a number of specialized formations, each of which solves its own tactical problem depending on the specific phase of the flight and the nature of the potential threat. One of the most common basic formations is the so-called finger four formation, which received its informal name due to the characteristic arrangement of the four planes, clearly reminiscent of the relative location of the tips of the four fingers of an outstretched palm when viewed from above. This formation, developed and actively used during the Second World War, provides an optimal balance between visual mutual control of all four aircraft of the group, effective mutual cover of the rear hemisphere, and sufficient tactical flexibility for rapid separation into two independent, but still interacting pairs in the event of a direct air battle. The so-called combat open formation, combat spread, has a different character, in which the planes of the group are located at a much greater mutual distance from each other compared to a dense formation, providing a significantly better mutual visual and radar overview of the entire group of the surrounding airspace, which is especially important precisely in conditions of a real, urgent threat of a surprise enemy attack, requiring the fastest possible mutual detection of such a threat by any of the group members. There is also a fundamentally different type of formation, used primarily during flights in peacetime or at a stage when the immediate threat from the enemy is considered minimal. A dense, compact formation that greatly facilitates visual navigation, especially in difficult meteorological conditions with limited visibility, and simplifies certain joint maneuvers, such as the previously discussed group refueling in the air, which, on the contrary, requires fairly close mutual location of the group's aircraft for effective coordination of the refueling process itself. The choice of a specific type of group formation at each specific moment of the flight is determined by a number of factors, including the current phase of the mission being carried out, the current assessment of the level of threat from a possible enemy in this particular airspace, current meteorological conditions, and specific tasks that the group will have to perform in the very near future. For example, a direct transition to attack a ground target, a likely engagement in an air battle, or, conversely, a relatively calm transit flight to the area of the main combat mission. It is important to understand that the transition between different types of formation does not occur chaotically, but in accordance with clearly established standard procedures, repeatedly practiced in exercises, allowing the entire group to synchronously, harmoniously, and predictably for the rest of the group members change the mutual formation almost instantly with a sudden change in the tactical situation, without creating the risk of mutual collision of the group's aircraft in the process of such a rapid restructuring. Mastery of group tactical interaction, including fluency in the full range of such standardized formations and the ability to instantly and correctly assess which specific formation is most appropriate to use in the current, often rapidly changing tactical situation, is considered one of the most important, although often least noticeable from the side of a non-professional observer, elements of the real combat effectiveness of modern fighter aircraft, the significance of which goes far beyond the individual piloting skill of an individual pilot. We have already examined in detail the technical evolution of ejection seats, including the modern 00 characteristic. But behind a significant part of this technological evolution is a specific company, largely unique in its corporate culture, the British Martin Baker, whose ejection seats are currently installed on combat aircraft in dozens of countries around the world, including a significant part of American military aviation. The history of the company has a very personal, tragic origin. The company's founders, engineers James Martin and Valentine Baker, initially focused on developing conventional aircraft rather than rescue systems. However, the death of Valentine Baker in 1942 during a test flight of one of the aircraft being developed by the company prompted James Martin to refocus the company's main activities on the development of effective systems for rescuing a pilot in an emergency, a task that at that time, at the height of the Second World War, was acquiring increasingly acute practical significance as the speeds of combat aircraft rapidly increased, significantly exceeding the physical ability to safely escape from a damaged aircraft the traditional way, simply by manually jumping out with a parachute. The company maintains a very unusual corporate tradition for such a highly specialized technical industry, maintaining detailed records of each real case of successful saving of a pilot's life using an ejection seat from this particular manufacturer, with each such case being assigned an individual serial number in a special informal club of saved lives of the company. Pilots whose lives were actually saved by the successful deployment of a company's ejection seat in a real-life emergency are traditionally invited to join such an informal club, receiving a special commemorative insignia and a personal letter of congratulations from the manufacturing company itself, a very unusual, deeply personal tradition for a company operating in the defense industry, which is usually much more impersonal and formalized in its external communications. Since its inception, the company has documented many thousands of similar cases of successful lifesaving of military and, to a certain extent, civil test aircraft pilots around the world, which, according to the company's own statement, serves as its main, most significant practical confirmation of the effectiveness of more than 7 decades of continuous engineering work to improve crew emergency rescue systems. The constant improvement of the design of the company's ejection seats occurred largely on the basis of a detailed engineering analysis of each real case of using the seat in an emergency, including both successful cases of rescue and, no less important from an engineering point of view, rare cases of unsuccessful operation or injury to the pilot during the ejection process. A detailed analysis of the reasons for which invariably led to further design modifications and improvements to the next generation of ejection seats produced by the company. The story of this company is a very significant example of how a tragic personal loss can become a catalyst for the creation of technology that subsequently saved many thousands of human lives, as well as a clear demonstration of how deeply personal, and not exclusively formal technical, the attitude of individual engineers and entire companies can remain in the development of critical safety systems, the effectiveness of which directly affects the lives of specific, real people. If the first generations of jet combat aircraft were built primarily from aluminum alloys, and then, as speeds and associated temperature loads increased, titanium began to be used more and more actively, then modern fifth-generation fighters are a much more complex, hybrid design, or a noticeable, and sometimes the predominant share of the total airframe mass is no longer made up of traditional metals, but carbon fiber-based composite materials. What are the real practical advantages of such composite materials compared to traditional aircraft metals, and why did their use in military aviation spread relatively later than in some other areas, including, for example, certain segments of the civil aircraft industry? The key practical advantage of carbon composites is the material's exceptionally high strength-to-weight ratio, significantly exceeding that of most traditional aircraft metal alloys. This makes it possible to achieve a noticeable reduction in the total weight of the aircraft airframe while maintaining, and in some cases exceeding, the required structural strength indicators, which directly translates into improved flight characteristics, longer flight range, higher maneuverability, or increased payload with the same total aircraft weight. Another significant advantage, which we have already touched upon in detail in the context of a general conversation about stealth technology, is that composite materials, unlike metal, are initially not such a pronounced reflector of electromagnetic waves in the radar range, which makes them a fundamentally more convenient, initially more favorable base basis specifically for the further integration of various radar-absorbing structures and coatings, which we also discussed in detail earlier. There are, however, certain practical difficulties that explain the relatively slower and gradual introduction of such materials in military aircraft construction compared to some other industries. Composite materials are much more difficult to respond to prompt, field repair in the event of combat damage compared to metal casing. Simple mechanical damage to a composite panel often requires a much more complex, technologically demanding repair procedure than similar damage to traditional metal casing, which in certain cases can be quickly repaired using much simpler methods directly in the field, without the need for complex specialized equipment. Another significant difficulty is associated with methods of non-destructive testing of the actual technical condition of composite structural elements during operation. Microscopic internal damage to the structure of the composite, such as delamination of individual layers of material under the influence of an impact or significant mechanical load, is often much more difficult to reliably detect by visual inspection compared to similar damage to traditional metal, which requires the use of specialized, often very expensive methods of ultrasonic or other instrumental monitoring of the condition of the structure. The modern approach to the design of a combat aircraft, therefore, is by no means a complete, uncontested transition exclusively to composite materials, but rather a thoughtful, engineering-based combination of various materials used precisely in those specific structural elements of the airframe where their specific individual properties are most in demand. Composites are mainly where minimizing weight and radar signature under relatively moderate mechanical loads is critical, while titanium and special high-strength aluminum alloys are still widely used in the most loaded, critically important from the point of view of structural strength, power elements of the airframe, including engine mounts, landing gear and other components that experience particularly significant mechanical loads during aircraft operation. Technologies will continue to develop. And this story, without any doubt, will have a continuation.